So, good evening, everyone. I'm Calvin Joseph, and I'm a research scholar at the IIT Kharagpur. And I'm today going to conduct the week 6 problem solving and doubt clearing session for the course Electrical Measurements and Electronic Instrumentation, which was taught by Professor Abhishek Chatterjee of IIT Kharagpur. So, today I will touch these topics. So, I will consider what is a current transformer, what is a potential transformer, what are the errors which happen when we use a CT and PT. Then I will also touch regarding some topics which Sir has taught in digital electronics. They include what is a SR flip-flop, D flip-flop, P flip-flop, what does it mean to be edge triggered or to be level triggered, or and how to make a counter, etc. We will consider. Okay, and then also we will solve some example sums. So this is for week 6. So this instrumentation transformer, like instrument transformers. So there are two types. One is a CT, one is a PT. So CT is a current transformer, and it is used to measure very high current. So suppose we have a current flowing through a line. What we will do is, like it is flowing through this line, like this, the current is flowing. Let us say from one transmission line to another transmission line, there's a huge, large amount of current flowing. Let us say like around 1 kiloampere current is flowing. Now we need to measure this current. So for what purposes would we require to measure current? Can anyone tell? Chittur and Niranjan? See, why do we need to measure current? Practically.
For observation purpose.
Okay, observation purpose. Okay, for measuring. So you have said, yeah, protection is a very important thing. So one is we want to measure measurement of the current. So observation and measurement are the same. Like you want to know how much current is flowing. Another thing is protection. If there is a fault, what if there's a fault, what we don't want the high current to flow and damage the costly equipment. Okay, so that's why these measured quantities of current are connected to some relays or to some logic functional things. So they will decide whether we must allow that current to flow, or we must open the line so that the current will stop flowing, or it can be used for measuring how much power is flowing, etc. Okay. So what we do is we will connect a current transformer. So this is a current transformer, and then it has a core, and then this is the secondary. And across the secondary, we connect an ammeter. So let the number of turns here be N1. Let the number of turns here be N2. Okay. So is this a step up or a step down transformer?
A step up.
Yes. So it is a step up transformer. Yeah. So it is a step up transformer, and I've tried to show it in the drawing because N2 is greater than N1. Okay. So for a transformer, we know that the voltage V2 upon V1 is equal to N2 upon N1. There's another relation. This is for ideal transformer. There's another relation, that is I1 N1 is equal to I2 N2. So now what do we know? My I1 is very large. I1 is very large. And what I want is my I2 to be low. Okay, I want my I2 to be low. So my N2 will be greater than my N1. Okay. So this I1 N1 should be equal to I2 N2 in the ideal sense. So this ammeter says it can measure current only between 0 to 10 ampere. So the current over here, the maximum current over here can be 10 ampere. And here 1 kilo ampere, that means 1000 ampere is flowing. So what should be my N2 and N1? Let us say N1 is actually 1 ton. Okay, N1 is 1 ton. So what should be my N2?
1000.
So my N2 should be 1000. Okay. My N2 is 1000. My N1 is 1. My I1 is 1000. But my I2 is 10 ampere, no? Then my N2 cannot be 1000. My N2 should be 100.
Right, sir.
Because my I2 is 10 ampere, my N2 should be 100. Because my N1 is 1. Okay. So any doubts in this? No doubts?
Sir, I have a doubt, sir.
Okay. Tell
Sir,
them.
if there is one, sir, if there is 1 kiloamps flowing in the primary side,
Mm-hmm.
then in the on the secondary side, as current is stepped down, but the voltage is steps up very high. So how it's practically possible, sir?
Okay, okay. That's a good question. Okay. So now, um, let us consider a model of a transformer. A model of a transformer is not required. Mm. Okay, I'll have to use the model of a transformer. So let us consider the equivalent model of a transformer. Okay. So what does a transformer have? This is, let us say, my input, V1. Okay. There will be some R1. There will be some J omega L1. There will be my R0. There will be my XM. Okay. Then there will be R2, J omega L2. And then this is the ideal transformer part. Okay, this is the ideal transformer part. Okay, where there's N1 turns and N2 turns, etc. So now the current transformer is connected to an ammeter. So this is my ammeter, right? So what is the resistance of an ammeter? Internal resistance, let us say the internal resistance of my ammeter is 10 ampere. Okay, it is 10 ampere. That is, this ammeter has a resistance of, sorry, not 10 ampere, 10 ohms. Sorry. Okay, it is 10 ohm. So instead of the ammeter, we can replace it by a resistance of 10 ohm. Okay. So how does this, so what is the voltage drop over here? And the maximum current that the ammeter can connect is 10 ampere. So suppose 10 ampere current is flowing. This is I2. I2 is 10 ampere. So what is the voltage drop over here, V2? What will be the voltage drop?
100.
So my V2 is equal to 100 volt. Okay. Now what will be my this voltage over here? E1. What will this voltage be? E1.
Very high voltage.
Okay, we will see. So we know E1 upon V2 is equal to N1 upon N2, right? So my E1 is equal to V2 into N1 upon N2. So what is my N1?
100.
No, N1 is 1 turn.
N1.
My N2 is 100 turns.
Sorry,
So
sir.
my E1 becomes equal to 1 volt. Okay, so my E1 is equal to 1 volt. So my V1 will be little bit, V1 will be slightly higher than E1. Okay, so that is why this drop over here is very low. It is like approximately 1 volt. Okay.
Yes, sir.
Hmm.
Sir, what about in potential transformer, sir?
What about?
In potential transformer, sir.
We will look in potential transfer also. Okay. So till this part is clear, right?
Yes, sir.
Okay. So one more thing I want to point out is this R1 J omega L1. So what is this? What do they represent?
Part.
What does R1 and J omega L1 represent?
Losses, copper losses.
Okay. So we know a transformer, there's a core, there's this winding, right? This is carrying I1, there are some N1 turns. It's carrying current I2 and N2 turns. So in this winding, these windings, these windings will have some resistance. They will have some resistance, right? So that resistance will lead to losses, ohmic losses. Similarly, all the flux which it generates, some flux instead of linking with the core will link with the air. Okay, so that is known as leakage flux. So that leakage flux corresponds to this L1. Okay. Then my XM is the magnetizing in the current. So XM will carry the current which is known as IM. This IM is the magnetizing current. Similarly, this R0 stands for the core loss. That is the losses in this core. That is hysteresis loss, eddy current loss. All that we represent by a R0. Okay. And that will carry some current I0. All right. And this is my current I1. And this is my current I2. So in a practical transformer, we cannot have this relation that is I1 N1 is equal to I2 N2. This is not possible. Why? Because this I1 is getting divided into I0 and IM plus some I2 dash. What we can have is I2 dash N1 is equal to I2 N2. But we cannot have I1 N1 is equal to I2 N2. Should I repeat again or there are some queries? Because this is a very important concept about what does a transformer actually represent. Hmm. So there is this drop due to the resistance and leakage inductance. There is some current which will flow because of the core loss and because of the magnetizing current which is required to set up the magnetic field in the transformer. Then there's another drop, voltage drop, which is due to the resistance and leakage inductance of your secondary coil. Okay. So all these drops, they are the non-idealities. So because of these non-idealities, this relation, that is, this is not practically possible, neither is this relation practically possible. So what is causing the deviation? What is causing the deviation is this. In the current transformer, we want I1N1 to be equal to I2N2. This is a desirable condition. But what is happening is, we are getting I2 prime N1 is equal to I2 N2, right? So what is happening? This I0 and Im is the cause. I0 and I, because I0 and Im is there, that is why my I1 is not equal to I2 prime. And so if my I0 and Im is small as possible, then my I1 will approximately be equal to I2 prime. Okay. And if that is possible, then my current transformer is as close to the ideal condition as possible. But that is very rare to happen. Okay. One more thing is, if we apply KCL over here, we apply KCL. What do we have? I1 bar is equal to what? I core loss bar plus I magnetizing plus I2 bar. Okay, the bar represent phasors. Okay, these are all phasor addition. So we have this I1, then there's certain I0. So this I0 plus Im bar can be represented as current IC. So IC is a combination of the, sorry, this actually is IC, this actually is I1. Sorry. This current is your IC, this current is your I0. Okay, approximately your no load current. So, sorry, so this will be IC. So we can write I1 bar is equal to I0 bar plus I2 bar. We just add these together, it becomes my I0 bar. I0 bar is also known as my no load current because it is the current which will flow when the transformer is at no load condition. So we have an I1 bar and an I0 bar. So then suppose this is my I2 bar. And then this is my I0 bar. Okay. So this is what is relating. There are two errors which are happening. One is my ratio error. One is my ratio error. What is the ratio error meaning? This I2 prime. My I2 prime upon I1 is not equal to 1. This is one error which is occurring. Or what is my I2 prime? I2 prime is equal to N N2 upon N1, I1 upon I2, right? So my N2 I2 upon N1 I1 is not equal to 1. This is the ratio error. Second is known as the phase error. What is the phase error? It says that I1, sorry, I2 is not in phase with I1. Because I2 is, there is certain phase shift, and this phase shift is not good, because this phase shift will create a problem when we do something known as energy measurement, energy or power measurement. This will result in error. Okay. So any doubts? Or you guys want me to give a recap? Sorry?
Clear, sir.
Yeah. Okay. Okay. Fine. All right. So this is for current transformer. Next we'll consider potential transformer. Or known as PT. So potential transformer is used to measure very high voltage. So suppose there is a line which is carrying a very high current. Let us say our 1 kilo ampere current is flowing. There's another reference point or my ground. And the difference in voltage is, let us say, 1 kilovolt. Okay. We want to measure it. So what do we do is connect a potential transformer. Which is connected to a voltmeter. Okay. So this will give the reading. And this will, let us say, N1. This say N2. So for a potential transformer, do we require a step up transformer or step down transformer?
Step down.
So
Step
we
down.
require a step down transformer. That would mean my N2 should be less than N1. Correct. So my N2 should be less than N1. So let us say this is my V1 and this is my V2. So my V2 will be equal to N2 upon N1 into V1. So let us consider some numbers. Let us consider my N2 is 500. And my, sorry. Let us consider my N2 is 2 and my N1 is 500. And my V1, we know it is 1000 volt. So what will be my V2?
Four.
Yes. So my V2 will be equal to 4 volt. Which is not very high. So that way I can measure very high voltage. I can measure to bring it very low. So this is the advantage of potential transformer, and also there is a safety. Okay. The voltmeter, first of all, we don't require a very high voltage voltmeter, and many of that is not practically possible. So what we are doing, we are stepping down the very high voltage to a low voltage where we can connect a practical voltmeter, and also that voltage is not too high, so it will not be harmful to the operator or person who is taking the readings. or the person who's making the connections. So there's the safety factor also, which is very important. So in electrical systems, safety is very important. So I'm guessing like most of you are bachelor students or working in the electrical domain. That is why you're joining these sessions to enhance your knowledge. So safety is very critical. Uh, it's like you may not get another chance in like in these power plants, etc. They have there's a motto which I read or which some worker told me is safety first. Safety first, duty later. Something like that. Because life is very important and you have to be very safe while doing these experiments. Huh. So you should always use what is like a fuse should be connected, and you must know what is on, what is off, which supply you must turn on first. Okay, all these things you must do so that the current which you flow is not too high, etc. All right.
Sir, I have a
There's
small doubt.
huh?
I have a small doubt, sir.
Yes, yes, yes.
Sir, when PT is connected in parallel, in
Mm-hmm.
secondary side of PT,
Mm-hmm.
according to the transformer action, power is constant, na, sir.
Okay, power is constant. Yes.
Then the secondary currents will be very high, na, sir. How can the potential, the voltmeter handle such high currents?
Okay. So this is a voltmeter. The internal resistance of voltmeter is very high. Okay, it is very high. Let us say the internal resistance is like 10 kilo ohm. Okay, it is 10 kilo ohm. So that means instead of the voltmeter, we have a 10 kilo ohm resistor, equivalent 10 kilo ohm resistor. So we found out that the V2 is 4 volt and there's a 10 kilo ohm resistance. So what will this current I2 be? Hmm?
4 milliamps. Like,
It is 0.4 milliampere, 0.4 milliampere.
sir.
Okay? 0.4 milliampere is flowing. Now, what will be the current which will flow over here then? First of all, what relation you must use? You must use the relation I1 N1 is equal to I2 N2. So what is the I1? Is equal to 0.4 into 10 to the power minus 3 into N2 is 500 divided by, no, N2 is 2, sorry. My N2 is 2 divided by 500. So how much will this be? You guys have calculated, right? So how much will this current be? 0.4 into 10 to the power minus 3 into 2 upon 500. Okay. In your NPTEL exam, you will get a gate calculator. You cannot take your actual calculator. And using gate calculator, it is a bit slow. So I'd prefer when you're practicing sums itself, you learn how to what you say, solve or do the mathematics or computation or calculations without using the calculator as much as possible, such that you will minimize the amount of time you use your calculator. So let us see how to make this calculation. First of all, I1, it is given here, 0.4 into 10 to the power minus 3 into 2 upon 500, right? What I can do is, I can write it as 4 into 10 to the power minus 4 into 2 upon 500, right?
1.6 microamps.
Yeah.
Right, sir.
I'll just show how to do it easier in the way. So this you can write it as 4, like 4 into 2 is how much? 8. So you write it as 8 into 10 to the power minus 4 upon 500. Now I want to make it easy. So what I do, I multiply this by 2, I multiply this by 2 as well. So I'm not changing the value. I'm just doing some multiplication which makes my life simpler. So what is 8 into 2 is 16. So this becomes 16 into 10 to the power minus 4 upon 1000, right? So this will become, so my I1 will become 16 into 10 to the power minus 4 upon 10 to the power 3. Now, based on the law of indices, this will become 16 into 10 minus 4 minus 3 because it is going to the numerator. So this becomes 16 into 10 to the power minus 7. Or I write it as 1.6 into 10 to the power minus 6 ampere. So it can be written as 1.6 microampere. So this looks long, but as you start solving and as you try to learn how to simplify and use these techniques, you can do it fast. Many of you will know it also, but I'm just giving a brief recap. So coming back to the question, someone asked, how much is the power? Power which is dissipated, right? That is a problem. So power is actually V1 into I1. So what you got your V1 to be? V1
1
also
kV.
calculate. Huh?
1 kV, na, sir?
Yeah. V1 is 1 kV. So yes, sorry. So V1 is 1 kV. So 1 into 1000. And current is 1.6 into 10 to the power minus 6. So that is actually 1.6 into 10 to the power minus 3. So the power dissipated is approximately 1.6 milliwatt, which is a very small fraction. Okay. So that's how the power dissipated by the potential transformer is very low. And that is why it is used. Now, if you see this, if you consider that this line, transmission line is operating at close to unity power factor and most of the current is in phase with the voltage, then the power which it is currently handling or transmitting is approximately 1 kV into 1 kilo ampere approximately. So it is approximately 1 megawatt. It will be lower than this if we consider power factor as well. But then approximately it can be 1 megawatt, okay, at the maximum. But the power which is used by the potential transformer to measure it is 1.6 milliwatt, which is very low, almost negligible. Okay, so that is the advantage of using a potential transformer. It is giving you safety. It is giving you safety as well as lower loss. Okay, so that's the advantage. So now, actually, I'm conduct these sessions on Zoom. So on Zoom, it has a 40-minute limit. So after the 40 minutes finishes, these sessions will end. Then I will restart the same meeting. So it is the same link. So you'll have to just rejoin the link, and and we can proceed with the further part of the section. Another part is another part is. So these are some links where driving is where I upload my notes. These notes, handwritten notes, I will make it into PDF and upload it on my drive. And the YouTube is where I will post these videos later for your reference. Okay, so I have added these links on the chat so that you can refer to it. Okay, to access the notes and the video later. So are there any doubts now? Okay. So we have studied the current transformer and potential transformer. In potential transformer also there is the ratio error. Which occurs. So this diagram is very important. You must understand this diagram properly. What we want is V1, what we desire. We want V1 upon N1 is equal to V2 upon N2. But that is not happening. In a potential transformer, why it is not happening? Because there are some drops. V drop, another V drop. So because of these drops, there is some potential which is applied, is lost in this part, as well as in this part. So the V2 is slightly lower than what we want. Okay, and that is resulting in the error. That is resulting in the error. Then another thing is known as phase error. So if you see this, we have V1, then we have V drop. Let us say V drop 1 and V drop 2. And this finally my V2. Okay, V2 is over here. So we can write V1 minus V drop 1 minus V drop 2 is equal to your V2. So what do we get is, suppose this is my V2. Then I will add V drop 1 here. Then I will add V drop 2. Then I will get my V1. So one thing is my V1 and V2 are not same. That is my V1 is not equal to V2. Similarly, my V1 is not in phase with V2. There is a phase error. And that is resulting in incorrect measurements. Okay. So we have studied regarding current transformer and potential transformer. What are the errors which occur in their measurement? And furthermore, sir has taught very important and interesting topic, which is known as digital electronics. Like the basics, sir has started. All right. So in the digital electronics part, we have, what is the main thing is we have like something known as data and logic. It is either true or false. It is either high or low. It is either 1 or 0. Okay. So it is either we can consider like say 1 or 0 or high or low, or it is true or false. Okay. There are many things. We can have what is known as an XOR gate. So what is an XOR gate? Suppose we have, this is an XOR gate. It has inputs A, B, let us say this is output Y. So we will make what is known as a truth table. You guys will know it, but for recap, so truth table is like this: 0 0 0 1 1 0 1 1. So for XOR gate for 0 0, what should be my output? Hmm?
0, sir.
Yes, it should be 0. For 0 1, what it should be?
1.
For 1 0,
1,
1, and for 1 1,
0.
1 1,
0.
right? So XOR gate, how to remember is when both are same. When both are same, you will get 0. Both are same, you get 0. When they are different, you get 1. Okay? This is how you get a XOR gate. So now, let us consider a SR flip-flop. We have one XOR gate like this, another XOR gate. Sorry, the XOR gate symbol, there's an error. This is an OR gate symbol. XOR gate. We'll have this. This means less.
Right, sir.
Hmm.
Right, sir.
So now we draw that on this. We have one input here, another input here. This is another output, this is another output. Let us say this output is Q, and this is, let's say this is Q1, this is Q2. Okay. Now I will take the output of Q2 and I will feed it back to the other XOR gate. I will take the output of the first XOR gate and feed it as the input to this second XOR gate. And this will be some signal. Let us say this is A and this is B. Okay, this is A, this is B. So now, what will be my Q1, Q2? Suppose I put at A. Let us say I put at A, I put 1. And at B it is 0. Then what will be Q1 and Q2? Suppose Q1
Q1
was
equal to 1, sir.
Q1,
Q1 equal to 0. 0.
Q1 will be 0.
Yes, sir.
Okay. Achha. Why? Okay,
बी में जैसे सर
B में जैसे
बी में जैसे 0 है तो मतलब इसका आउटपुट में मतलब 1 ही होगा सर Q2 में.
क्यों?
ना 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 नहीं.
Let us say we have before this Q1 was, or let us say Q2 was 1. Okay, Q2 was 1 and Q1, let us say it was 0. So if Q2 was 1, then what happens? This becomes 1 1, this becomes 0, this becomes 0 0, this will become 1. Okay, I'll show. Suppose your Q2 is 1, right? So this will become 1. So here it will become 1. 1 and 1 becomes 0. And this 0 comes here. 0 and 0 are not the same. So 0 and 0 are not the same, right? So since 0 and 0, 0 and 0 are the same, your Q2 should become 0. This will become 0. And this becomes 0. This will become 0. And 0 and 1 comes. This will become 1, right? And when this is 1, this will become 1. So this will become 1. And 1 and 0 will become what? Will become 1. No, it should be on oscillating. should reach some steady state value actually. Okay, let me draw on a fresh page because perhaps I'm making some mistake in a new page. So target. Hmm? This is my A, this is my B, this is my Q1, this is my Q2. This output is going here. This output is coming from here. Okay. Suppose my A is 1, B is 0. And let us say this had some value Q1 previous. This had some value Q2 previous. Hmm. So
सर
हाँ बोलो।
एसआर फ्लिप फ्लॉप मतलब एक्सओर गेट में भी अप्लाई करते हैं क्या कि एंड और नोर गेट में अप्लाई करते हैं सर?
नहीं XOR गेट यूज करते हैं यहाँ पे,
अच्छा
पर एंड और नॉट गेट को भी आप कंबाइन करके XOR गेट बना सकते हो, थोड़ा और कॉम्प्लिकेटेड रहेगा। ठीक है।
वो तो इजी था सर, वो तो
हाँ।
नोर और एंड गेट में हम देखे थे वीडियो इसका ये में।
ठीक है, मैं बता रहा हूँ। So if you have 1 and 0 over here, so this will be your Q2 previous, right? And we know from XOR gate, if it is 1, one input is 1, and your output is, and this is another input, so your output Y will be complementary. If A is 1, then your Y is B bar, right? So here your A is 1, your output is Q2 previous. So that means your Q1 previous will be equal to Q2 bar previous. Okay, so both of them are complementary. So if this is 0, this has to be 1. So that we have fixed. We have understood that Q1 previous will be the complementary of Q2 previous because of this XOR connection. Now let us assume Q2 previous is 1. If Q2 previous is 1, then that means over here is 1. So 1 XOR 1 is 0. Then 0 XOR 0 is 1, right? So in this case, there is no change. There is no change. Now what we will do is, we will make Q1 previous 1. This is 1 and this is 0. So if this is 0, that means this is 0 and this is 1. So this X. So 1 or 0 again becomes 1. I'll have to check this logic. So here I think I'm making an error. I will check this logic and I will clarify it with you guys later. Does anyone able to identify my mistake? Okay. So now let us say this gate A, B. Let me use the terms actually correctly. So this is my set, this is my reset. Okay. This is my Q bar, this is my Q. So this comes here and this comes here. So this is SR flip-flop. SR flip-flop. So the logic over here is this is RS, this is R, this is Q. And this is the Q bar, which is the complementary, which we already showed. So there are three cases. S can be four cases. S can be 0, R can be 0. This could be 0, 1, 1, 0, 1, 1. So if both S and R are 0, 0, then this will hold the value Q previous. But if S is made 0, if R is made 1, then regardless what was the Q previous, this will be made equal to 0. Regardless of what is the previous value, this will be made 0. But if set is 1 and R is 0, then this will become 1. Forced to become 1. But S and R, this is not possible, not allowed. Okay, this condition is not allowed. So this is for the SR flip-flop. This is the truth table. So now how do we write SR flip-flop? We write it as a symbol. We write as S, R, Q, and Q bar. Okay. So this is the symbolic representation of SR flip-flop. Now there's a problem is we cannot apply 1, 1. So what solution they came up with is we can what we can do is use a NOT gate in front of the reset. We put a NOT gate and we put input. If we do that, what will happen? We can only give this condition and this condition. We cannot give this condition is not possible and this condition also is not possible. We didn't want this condition to happen, so we connected this logic. But then we are also losing the ability to have this condition also. So then there came another flip-flop, which is known as the D flip-flop. Okay. Or D flip-flop. What does that have? It has this XOR gate, like the similar SR flip-flop structure. And it has an AND gate as well. So this is my set. This is my reset. And there is further an enable block. Okay. So what does the enable do is, no, SR, which is D flip-flop. Sorry. So D is my input. And then we have a NOT gate. We have a NOT gate, which is given here. So it is the same structure. It is just a modified version of the SR flip-flop. So the D flip-flop is given by D and enable, and then your Q. Okay, your Q. So what is the truth table of this? So if enable is 0 and D is 1 or 0, your Q will be Q previous. It will not change. But if your D If your enable is 1 and D is 1, you will get 1 over here. And if your enable is 1 and D is 0, you will get 0 over here. Okay, so this is the D flip flop. So now, so after the D flip flop, which are the flip flop did sir teach? Do you guys know? So there's another thing known as a T flip flop. It is made D enable and the Q. This is by the XOR of this Q and the input and the enable signal. Okay. So this is combinedly written as T and enable and Q. So the truth table of this is, let us say this is T and this is enable and this is Q. If enable is 0, regardless of what T is, it could be anything, your Q will not change. Your Q will be Q previous. But if your T is 1 and enable is 1, then Q will become Q previous bar. And if your T is 0 and enable is 1, it will be Q previous. No, sorry. If T is 1, your output Q will be 0. And if T is 0, your output will be 1. So it is flipped. It is made opposite. Okay, T flip-flop is made opposite. If your input is 1, your output will be 0. If your input is 0, your output will be made 1. Okay. So this is regarding flip-flops. So are there any doubts or should I proceed with solving the sums? Okay. Shall I proceed with the sums? Let us answer this question. So the primary side of a PT is connected to a high voltage line and the secondary side is connected to a voltmeter. So we want to change the voltmeter on the secondary side while the primary side is still alive. So primary side voltage is still on. Select the correct way of doing this. So which way is preferred or which way can be used? So what do we have? We have a high voltage line. This one line where there's high voltage. We have a potential transformer. And there is one voltmeter. They're saying there are two ways. One way is what? we will remove this potential transformer, and then we will connect another potential transformer. This is option A. What does option B do? Sorry. What is option B? Is there was this voltmeter V. Now we will connect another voltmeter, and then what we will do, we will remove this first voltmeter. So which method can we use? We can use both methods. So why we can use both methods is there is no problem if the potential transformer is left open circuited. Like in the current transformer, we cannot, in under any condition, allow it to be left open circuited. But in a potential transformer, that is fine. It doesn't cause much of an issue. So we can either remove the old voltmeter first. When we remove the old voltmeter first, what happens? The output becomes an open circuit. And then we connect the new voltmeter. It is still okay. Or else we can first connect the new voltmeter in parallel to the old voltmeter, and then we remove the old voltmeter. This also is fine. So it is both. Both of them are fine. Okay. Next. The question says, to reduce the ratio error in a CT, its magnetizing current should be what? Equal to the secondary load current, very high, very low, which is the correct answer. It should be very low. Why? Because this is the XM, this is the RM, this is the magnetizing current, this is your I1, this is your I2 prime, this is your N1, this is your N2, and this is your I2. So you want this current IM, this current to be zero. If this is zero or as low as possible, then current I1 and I2 will approximately follow the relation of I2 upon I2 into N2 is equal to I1 into N1. Otherwise, it will not follow. Okay. So that's why the magnetizing current should be very low. So this actually is the ideal transformer part. So why I always use this representation is because it is gives you insight into why we must not leave my transformer open circuited, why I should not leave my CT open circuited, why I need the magnetizing current to be low. This model helps you to understand that. That is why this is known as the equivalent circuit model of the transformer. So this part is an ideal transformer. In this ideal transformer, what do we have? We have I2 N2 is equal to I2 prime N1. What is I2 prime? It is a reflected equivalent current of the secondary in the primary. So this is valid. So this is okay. But what happens is this I2 prime is what? It is equal to this I1 minus this magnetizing current and all. So this is what is causing the error. What so effectively what do we get? We get I1 minus IM into N1 is equal to I2 N2. So we get this I1 N1 minus IM N1 is equal to I2 N2, but we don't want this. So this is what is causing the issue. So if we reduce the magnetizing current to be as low as possible, then I1 N1 will be equal to I2 N2. Okay. So we'll go to the next question. So the primary side of a CT is connected to a high ampere line, and the secondary side is connected to an ammeter. So we want to change the ammeter on the secondary side while the primary side is still live, that is carrying the current. So which way should we do? Should we remove the old ammeter first and then connect the new ammeter to the secondary side of the CT? If we remove the old ammeter first, what will happen? It will become an open circuit. And then we will connect the new ammeter. Or we must connect the new ammeter in parallel and then connect the old ammeter. Which is better?
B.
Yeah, we must first connect the new ammeter and then in parallel, and then we must remove the old ammeter. Hmm. We'll go to the next question. So while measuring a high voltage using a potential transformer and a moving iron voltmeter, which of the following may cause a measurement error? Will the ratio error of the PT cause the error or the phase angle error of the PT? Which will
रेशियो
cause?
एरर सर.
Why?
हाई वोल्टेज हम लोग मेजर करना है इसलिए.
हाँ, तो फेज एरर से प्रॉब्लम नहीं होगा, फेज एंगल एरर से. So this is for a PT, right? For a PT, I consider this is one error. Ratio error is V1 is not equal to V2. Phase error is V1 is not in phase with V2. So can the moving iron measure phase? Can it measure phase? Can a moving iron voltmeter measure the phase of a, what does a moving iron give? So the moving iron voltmeter will measure only the amplitude, or it measures only the RMS value. Okay, it doesn't measure the phase. So even though there is a phase error, but what happens is the voltage it measures is just the RMS value. And that is what happens is V1 is not equal to V2. This is the RMS value. In phase can be captured only when we have a phase measurement unit. Okay, which will measure the phase difference of phase shift. But we don't have. Okay. So the moving iron will measure only the RMS value and not the phase quantity or the phase information. So because it is only measuring the RMS value and the RMS value of the output is not equal to what we want as per our formula, hence there is a ratio error. Okay. So hence it can only measure the ratio error. The phase error will go undetected. Hmm. Okay, so we will consider this circuit now. So which is my set and which is my reset? Hmm? Any idea? So this actually is the set. And the one closer to Q is reset. So suppose we make this as 0 and 0. If both are zeros, then what will happen at the output? Suppose this had some value Q previous. This will be Q previous bar. So this will come over here as what? Q bar previous. Q bar previous plus 0. So these are NOR gate. So what is a NOR gate? 0, 0 is 1. 0, 1 is 0. 1, 0 is 0 and 1, 1 is 0. Right? So in this condition, A is all 0. So if B is 0, then my Q is 1. So if this is Q bar previous, this will be Q previous. Right? This is Q previous here. And this also is 0. So this will become Q bar previous. So it is retaining the old value. Now, let me make set as 1. Set is made 1. And this is Q previous. So if it is 1, if this is 1, okay, so this is a NOR gate. So in the NOR gate, what do we have? We have, let us say this is input 2 and this is 2 prime. So 2 prime and output is Q bar. So here input 2 is 1. Okay, this is Q previous. Okay, let me take a better way. So this is 0 or it could be 1. So for a NOR gate, if one of the inputs is 1 always, then the output will be 0. In any condition, it will be 0. In any condition, it will be 0. So regardless of whether this Q previous is 1 or 0, this will finally become equal to 0. And this is 0. It will come over here as 0. And 0 and 0 will become equal to 1. Okay. So that is how we get the output. So the error which I had made earlier was I considered all these to be XOR gates. These I consider to be XOR gates, but they are wrong. This is wrong. So all are wrong actually. These should be actually NOR gates. How Niranjan, you were saying, right? It should have been NOR gate, right?
Yes, sir. NOR और NAND gate, sir.
That is
use कर सकते हैं.
no. So I had made a mistake. I considered to be XOR gate, but actually it was NOR gate. Otherwise, it could
Yes.
have happened. So that's why all this was. It should have also been NOR. Should have been NOR gate. Here also replace XOR with NOR. Okay. So sorry, like some time got wasted in this. I made a mistake. So instead of XOR gate, it's a NOR gate. So this is how we found which is what output. Now let us consider the next condition. If I have my reset is 1 and my set is 0. And what is this QB? Let us say this is some Q previous. This is some Q previous bar. So we know for a NOR gate, if one of the input is 1, if this is the input is 1, then the output has to be 0. So whatever may be this value, because this is 1, this output will be 0. Now this is 0. This comes here. So 0 not 0 is how much? 1. So this has to be 1. Now this 1 comes over. So I hope it is clear. So if my set is 0 and my reset is 1, and then this will become 0 or 1. So this is the truth table. So effectively the truth table, what do we get? SRQ is, this is 0, 0. This will be Q previous. If this is 1, and this is 0, this will be 1. This is 0 and 1. This will be 0. Now what will happen if both are 1? If both are 1, what will happen? Let us say this also is 1. And instead of this being 0 and 1, let us say this will be Q previous. So 1 and Q previous will result in 0. Okay? Because this is, let us say this, so here 1 is there and some Q previous is there. Anything with 1, nor of 1 with anything becomes 0. Now this 0, nor of 1 will be what? 0 nor of 1 will again be 0. And 0 nor of 1 will again be 0. So what is happening is both of my outputs, Q and Q bar, both are 0, which is not permissible. We want Q and Q bar, they should be complementary. We want Q and Q bar to be complementary. But what is happening is if I put reset as 1 and set as 1, then both are 0. And that is not allowed. That is not accepted. That's why you cannot give set as 1 and reset as 1. That is not accepted. Okay. So now we will go to the next question. So this is a D flip-flop. Okay, we want to know whether it is level triggered, whether this negative edge triggered, or whether it is positive edge triggered. So first, let us draw and have the truth table of a D flip-flop. So there is D, there is enable, and there is Q. So if enable is 0, if D is 0 or 1, Q will be Q previous. That is, it will store. But if enable is 1 and D is 0, then it will become 0. If enable is 1 and D is 1, it will become 1. Okay. So this is the truth table of a D flip-flop, or one of the flip-flops. Let us say this is D1, this is Q1, this is enable 1, this is D2, this is enable 2, this is Q2. And this is finally my Q. Right? So now I give a clock. A clock is given like periodic signal of low, high, etc. Okay, this clock is very, very basic and used a whole lot in digital circuit. So you have main clock, and that clock will drive your other circuits. So let us consider this your clock. It goes high. If this goes high, what happens is this is disabled, because this is what? If this is 1, this is 0. That means this is disabled. And this is 1. That means this is enabled. So when your Q will be equal to Q previous. What is the Q previous? Was some Q1 which was there. Now, my clock goes from 1, it will go to 0. What happens now? This 0 will become 1 and this 1 will become 0. So now what does this do? Now this is disabled and this is enabled. So this will what it will do at this instant. What D is there? Your Q1 will be equal to D. Right? And that will further pass. So we will check whether it is triggered when it goes from high to low or low to high. So we will draw what is known as a timing line. So we will take this circuit. So this is my clock. This is my enable 1, enable 2, D1, Q1, D2, Q2. This is my, what is my enable 1? This is my enable 1. What is my enable 2? Sorry. This is my enable 2. My enable 2 is same as the clock, right? So now I have some data over here. Some data, let us say, some data which is going like this, falling, going like this, up, like this, like this, like this, and like this. This is my D. Now what will be my D1? When this is, when so my D1 is D. So what will be my Q1? My interested thing is Q1. So what is Q1? So as long as enable 1 is high, as long as enable 1 is high, my Q1 will be equal to D1 when my enable 1 is equal to 1. So what will I get as my Q1? I will get exactly D. I will get D. Okay, I'll get D. When enable 1 goes low, enable 1 goes low, what will be my Q1? My Q1 will be equal to Q previous when enable is equal to 0. So what will be my Q1 then? It will continue to be 0, 0, 0 to be. It will continue to be 0. Sorry, 1 minute. As long as enable 1 is low, it will continue to be at the previous value. Okay. Now enable 1 has become 1. But so enable 1 has become 1. So my Q1 is equal to D1. What is my D1 is D. That is low. So it will go low. It will go on low until my enable 1 becomes 0. When enable 1 becomes 0, my Q1 will be Q previous. Q previous is this. So it will continue to be 0. It will continue to be 0. Then it happens that what happens at enable, what happens over here is enable 1 is high. What is my D? D also is high. So it will go up. It will go high. It will go high. How long? I'm sorry. It will go high. And it will again go low. Because my D is changing. And D changes like this. As long as enable 1 is high, it will keep on changing as D changes. When enable 1 goes low, it will remain as it is. It will remain as it is. It will follow Q previous. Now let us see what happens at Q2. At Q2, what happens? When enable 2 is high, Q2 is equal to Q1 when enable 2 is 1. And Q2 is equal to Q2 previous when enable 2 is equal to 0. So enable 2 here is high. At this instant, enable 2 is high. So my Q2 will be high. Okay, it will be high. It will be high, right? As long as my enable 2 is on. Now enable 2 turns off. And Q1 at that time becomes 0. When my enable 2 turns off, my Q1 at that instant becomes 0. So it will also become 0 because at that instant it becomes 0. And then it will hold on to its previous value. Then when enable 2 becomes high, it will still hold on to the previous value. When enable 2 becomes high, it will take the value of Q1. So it will go like this. It will go like this. Okay. Next, when enable 2 goes slow, it will hold to the previous value. It will hold that value again. Then when enable 2 becomes high, it will take the value of Q1. Q1 is 1, so it will hold on like this. And then when enable 2 goes low, at that instant, what value of Q1 is there, it will store. Okay, so it will store that value. So effectively what is happening is Q2 is taking this data of D at this falling edge of this clock. At the falling edge of the clock, only its data is changing. One minute. Sorry, there was a mistake here. So when enable 2 is high, Q2 is equal to Q1. Okay, so it will continue to remain at this. When enable 2 goes low, then it will store what was the previous value. It will go high. So at this edge, what happens? That value will store. So let me just totally change this a bit. This is causing the confusion. Yeah. So now, let me repeat what is happening. So when the clock is high, enable 1 is low, enable 2 is high. And this is my D is my input. So this is my input and Q2 is my output. Okay. So let us say at this instant, enable 1 is high, it is some value. Clock goes high, enable 1 is disabled and enable 2 is enabled. So when enable 1 is high, what is the D input? Comes as Q1. When enable 1 is low, it will hold on to the previous value. So it will go on holding on like this. Okay. When enable 1 goes high, then what will happen? Whatever the D input is there will come. So it will become 0. So it will become 0. When enable 1 goes low, it will hold on to the previous value. So it will continue going low. Huh? Then, this is where I made the mistake. So then when enable 1 becomes high, then only this Q1 will become high. So although this has gone high over here, this will go high only over here. Okay, it will go high only over here. So because at that instant only the enable 1 has gone high. So when the enable 1 goes high, this Q1 will go high. So when Q1 has gone high, it will hold on to the D as long as enable 1 is high. When enable 1 goes low, Q1 will hold on to its previous value, it will go on like this. Now let us consider for Q2. So Q2 is on only when enable 2 is on. So when enable 2 is on, it will take directly Q1, it is on. When enable 2 goes low, then Q2 will hold on to its previous value. Right? So at this instant, your Q1 is going low, so your Q2 also will capture it. So your Q2 again goes low. Then this instant, when your Q1 goes high, Q2 will take that value. So it is changing as such. So whenever there's this negative edge, the value of Q2 is changing. Okay. So that is why it is known as a negative edge detector. So any queries? So now we'll proceed. So the next question. So we have a PT, okay? We have a PT. It is measuring some low voltage. So this is, let us say, 1000 volt. And we have a voltmeter whose range is 0 to 20 volt. And its internal resistance is 1000 ohm. So now we have to use a suitable PT to change the range of a voltmeter. Okay, we have to assume this PT to be an ideal transformer. So this has some N1, this has some N2. So my V2 is 20 volt, my V1 is 1000 volt. So what will be my N2 by N1? What will be my N2 by N1?
500 by 1.
Yeah. It will be 1000 upon 200. So be
No, sir. No. उल्टा हो गया सर. 1 by 500.
upon 1000. So that's actually 1 by 50. It's actually 1 by
Yes, sir. Yes, sir.
So in the question, what are they asking? Estimate the power in watt that will be consumed by a PT and voltmeter arrangement when measuring 1000 volt voltage. And we also have to find the equivalent resistance. Okay. So over here, my voltage at V2 is 20 volt and my internal resistance is 1000 ohm. So what is this current that is flowing? What is the current I2? this current I2 is actually my V2 upon my R internal resistance.
0.02.
So it is 20 upon 1000. So 0.02 ampere. So what is the power which is dissipated? Is V2 into I2. That is 20 into 0.02. That is equal to how much?
0.4.
0.4 watt. Okay. Next is we have to find the equivalent resistance. So now this is my transformer N1. This is my N2. And the voltmeter is looked as an internal resistance of 1000 ohm. So over here, what will be the equivalent resistance which is seen? Okay, that is what is the question. So this is my I1, this is my V1, this is my I2, this is my V2, right? Any problems in this till now?
No, sir.
So what do we know?
40 आ रहा है सर.
My
40
V2
आ
is
रहा है सर.
50 आ रहा है ना?
40 आ रहा है. 40.
40.
Yes, sir.
Making it to be 40. Okay, we will derive. Let us see.
Okay, sir.
So I know my V2 upon V1 is equal to N2 upon N1. Or my V1 upon V2 is equal to N1 upon N2. Because it is ideal transformer. Similarly, we have I1 N1 is equal to I2 N2. So my I1 is equal to what? I2 N2 upon N1. And my V1 is equal to what? V2 into N1 upon N2. So now what do I do? V1 upon I1 is equal to what? V2 into N1 upon N2 upon I2 into N2 upon N1. That is equal to V2 upon I2 into N1 upon N2 square. Okay. So V1 upon I1 is my R equivalent and V2 upon I2 is my R internal resistance. So that is my N1 upon N2 square. So what is my Rn? That is equal to 1000 ohm. What is my N1 upon N2? My N1 upon N2 is equal to 50 upon 1, right? So this is equal to 50 upon 1 per square. So my R equivalent is 1000 into 50 square is 2500. So it is actually 2500 kilo ohm. Okay.
Okay, sir.
This is 2500 kilo ohm. So now we have to consider this question. So we have to find out how many
Sir,
people.
R equivalent equal to क्या था sir?
2500 kilo ohm.
N1 by N2. How much, sir?
N1 by N2 50 na?
$50 और 150 sir. 1 by 50.
50 ना, क्योंकि यहाँ पे देखो ना, आपका N2 by N1 is 1 by 50. So your
Right, sir.
N1 by N2
Right,
is
sir.
equal to 50 by 1. Okay.
Right, sir. मतलब सेकेंडरी तरफ ये ट्रांसफर किए ना सर, ये प्राइमरी साइड में ना,
सेकेंडरी से
R को?
प्राइमरी ट्रांसफर किया.
यस सर.
इसलिए.
यस सर.
So now we have to consider how many T flip-flops are required to generate a 2 kilohertz square wave from a 16 kilohertz clock using a binary ripple counter? Okay. So what does a T flip-flop do? We have a T flip-flop. Okay, this is T. And this is my. So what does a T flip-flop do? If I give here 1, it should give 0. If I give here 0, it will give me 1. Okay. But this has to be done using a clock. No, T flip-flop doesn't have any input available. Just as an enable, which is your clock. Okay. So now this is your input clock. Okay. What it does, suppose this is a negative edge triggered. So negative edge triggered will be given by the symbol. It will change its value only at the negative edge. So suppose it was high. It was high. Then the negative edge, it will go low. Then the next negative edge, it will go high. The next negative edge, it will go low. Okay. So what does your toggle flip-flop do? Is it can just change its value. From 1, it will go to 0. From 0, it will go to 1. So actually, this is a wrong notation. So this is your toggle flip-flop. Okay. And this is your clock. And this means it is falling edge trigger. And this is your Q. So when your clock edge goes down, so this is your clock. When it goes down, this will go change its value. So this is your Q1. Next, we will connect this to another T2 and this will be its Q2. So when this goes low, this will change its value. Say its value also was 1. This will go to 0. And then when this goes low, it will change its value to 1. So if this has a frequency, this time period is how much? It is T. This time period is 2T. So this Q2 will have a time period which will be equal to 4T. It will go on. Okay. And Q3 will have a time period which is given by 8T. Okay. So if your clock had frequency of 16 kilohertz, what was its time period?
One by 16 kilohertz.
It's 1 by 16 kilohertz. So it is 1 by 16 milliseconds. So for Q3, its time period is 8 into T. That is equal to 8 upon 16 milliseconds. So it is equal to 0.5 millisecond. So its frequency is equal to 2 kilohertz. Okay. So that is how we have to use another flip-flop T3 and Q3. And this clock will have a frequency of 16 kilohertz. This output will have a frequency of 2 kilohertz. Okay. So we will go to the last question. So we have a CT. Carrying 1000 ampere. And there's an ammeter in the range of 0 to 10 ampere. So your I2 and its maximum is 10 ampere. And this internal resistance is 10 ohm. And we assume the CT to be an ideal transformer. Okay. What are they telling us to find? What is the power and what is the equivalent resistance in milliohm? Like the same thing which we did for the potential transformer. So what is the power? It is equal to I2 square R internal, 10 square into 10. So that is equal to how much?
1000.
1000 watt. Okay.
1 watt.
No, 1000 watt, no? 1000 watt.
1 kilowatt. 1
1
kilowatt.
kilowatt. 1 kilowatt. This is also quite a lot. Okay. Now this is resistor Rin. So the reflected R equivalent resistance seen over here is equal to Rin into N1 upon N2 square, right? The same formula we got over here, N1 upon N2 square. Now what will be N1 over here? What will be N1 upon N2?
100 by 1, sir.
100 by 1. We have
Yes, sir. 1000 by 10, sir. I1
we
by
have
I2.
I1 N1 is equal to I2 N2. So my N1 upon N2 is equal to I2 upon I. Right. So my N1 upon N2, what is my I2? Is 10. I1 is
10.
1000. So this be 1 by 100. Right? Any doubts?
No, sir.
So my R equivalent is equal to Rn. What is my internal resistance? 10 upon 1 by 100 square. So this 10 upon 10,000. That is equal to 1 upon 1000. So my R equivalent is equal to 1 into 10 to the power minus 3 ohm. So my R equivalent is equal to 1 milliohm. Okay.
Okay, sir.
Okay. So actually, I have made a mistake which I realize now. So I'll rectify it. This should not be like this. This is actually error. T flip flop also. So T flip flop has T and enable. Enable is where the clock will come. Okay. This is Q1, T1, T2, Q2, enable 2, T3, Q3, enable 3. So your T1 is initially connected to some high it is. Okay, it is high. This is your enable which gets your clock. This Q1 gets connected to the enable 2. And this T2 also is connected to high. And this Q2 gets connected to enable 3. And this is also connected to high. And this is your Q3. So the T flip-flop truth table, this is higher, this is high. This means it is 1, effectively 1. This is 1. Okay. So the truth table of a T flip-flop is, let us say, let me write it somewhere. some space here. We shall write it down here. The truth table of T flip-flop this is T, this is enable, and this is Q. Or enable or your clock. So when this is 0, when your T is 0 and your enable can be either 0 or 1, your Q will remain at Q3 years. But when your T is 1, and when your clock comes, okay, your Q will change its polarity. So T flip-flop can only be event triggered. It can only be event triggered. Okay. Only when there is an edge. It can either be a positive edge or it could be a negative edge. Only on that, depending on the T flip-flop. If we say that the T flip-flop is negative edge triggered, means when the edge falls, when your clock falls, at that time only it will change its value. And that will happen only if your T, at the T signal, it is connected to high. When your T is connected to high, then only that can happen. Okay. So this actually is a binary ripple counter. So this is at 1. So this is always, T is always on. So when clock comes at the falling edge of that clock, then only it will change its value. So when this clock falls, then Q1 changes its value. And then when the clock again falls, then Q1 again changes the value. But for Q2, but for T flip-flop 2, what is the clock? Is Q1. So when Q1 falls, then Q2 will fall. And then only when the next time Q1 falls, then Q2 will change its value again. Q2 is changing its value again. For Q3, what happens? Q2 is the clock. So when Q2 will fall, then only Q3 will change its value. So this is our T flip-flop can only be event triggered. It cannot be level triggered. Okay. Any queries? Okay, so I'll do a recap what we have done today. So first, I talked about instrument transformers. CT, current transformer, how it is connected in your line, how it is used for measurement, for protection, for fault, etc. How it is actually a step-up transformer. Then, what is the equivalent model of a transformer? What is desired, but what, because of these non-idealities, how the desired condition is not met, that I've shown. How the ohmic losses are there because of the resistances, and their inductances is due to the magnetic flux leakage or to represent the magnetizing current. How there's something known as a ratio error. There's something known as phase error. There are two types of errors, ratio error and phase error. So moving iron instrument, which will measure only the RMS value, will face the problem of ratio error. The phase error will come into picture when we want to do energy or power measurement. So what is power? Power, it is equal to V into I into cos phi, right? Now, if that phase shift, which is measured by your current transformer and your potential transformer is different, it differs, then your measurement will have, there will be an error, and your computation, your calculation of what is the energy or what is the power being used will be wrong. Okay. So that is a problem. Then we consider potential transformer PT, how it is a step-down transformer. We considered some values, how it is good for safety, and the fuse also will be there. Then how the effective reflected resistance is very high and how the power dissipation is very low. Again, here there's the ratio error. Again, here there's the phase error is there. Then we consider digital electronics. We consider the truth table of the XOR gate. Then I had made a mistake in the SR flip-flop. It should have been a NOR gate, not an XOR gate. and that caused a lot of confusion, which wasted a lot of time. Then I also considered D flip-flop, and then I also considered T flip-flop. Okay. So here, instead of the XOR gate, it should be replaced by a NOR gate, and then it will be a D flip-flop. It will be a D flip-flop then. So what does the D flip-flop do? When your enable is 0, it will, if your enable is 0. So let me rub this circuit. Delete. This is my D flip-flop. So this is my NOR gate. Okay, this is the NOR gate. So what happens is, when my enable is 0, when this enable is 0, then 0 will come here and 0 will come here. And this will be 0 and this will be 0. So effectively my set and my reset is 0. If my set and my reset is 0, what will be my Q? My Q will be Q previous. Okay. So if enable is 0, which is a truth table, my Q will be Q previous. If D is 1 or D is 0, my Q will be Q previous. Now let me make my enable 1. I'll make my enable 1. So if this is 1, what will this be? This will be D. And this will be D bar, right? So what will come accept this D? And if D is 1, okay? Now let us consider. If D is 1, let us say if D is 1, and then this will be 0. So if set is 1, reset is 0, what will become Q? Q will be 1. Now let us consider another case. When D is 0, if D is 0, what is my D bar? My D bar will be 1. Then what will be my Q? It will be 0. So SR flip-flop is a building block in which we added some configuration and changes, and we got a D flip-flop. So what do you get as D flip-flop? If enable is 0, Q will have Q previous. If enable is 1, and if D is 1, then my output Q will be 1. And if D is 0, my output will be 0. So this is the truth table for a level trigger. It is a level triggered D flip-flop. Okay, it is a level triggered D flip-flop, and this is a truth table of this. Okay. Next, what do we have? Is we have what is known as a T flip-flop. So T flip-flop is made by combining a D flip-flop and an XOR gate. So what happens if enable is 0? Then what happens? The D flip-flop is forced in the D. When enable is 0 and it's a D flip-flop, Q will be Q previous, right? So Q will hold on to the previous value as we showed in the D flip-flop. So enable is 0, Q will be Q previous. Now enable is made 1. Okay, enable is made 1. Q will have some value. That value will come here. That value comes here. Let us say 1. This is not distinct. Let us say this is. Say this is. Let us say Q was. So enable is 1 and Q is 1. So this comes out to be 1. Right? and my input at that time goes high. So if both are 1, 1, then what will come over here? It will come out to be 0. Right? It comes out to be 0. And when this is 0, D is 0, then Q will again become 0. So this is a problem with the T flip-flop if it is level triggered. So it has to be event triggered. So what is the event which will trigger it? Because now what will happen, the T flip-flop will continuously change. It will go from 0 to go 1, from 1 it will go 0. So it has to become what is known as a event triggered T flip-flop. So T So what actually is happening is, if this input over here or this signal over here is 1 or it is high. If this is high means in a XOR truth table, what do we have? In the XOR truth table, which I considered for XOR, let me consider again A, B, Q, 0, 0, 0, 1, 1, 0, 1, 1. In this case, it is 1. In this case, it is 0. Sorry. In this case, it is 0. In this case, it is 1. In this case, it is 1. In this case, it is 0. So when one input is only 1 all the time, then B will be what? Your Q will be equal to B bar. So this is the concept. So in the T flip-flop, what happens is, this IN1 will be connected to high, or it will be 1. It has to be 1 all the time. Then when you're, and this enable will change its value. Depending on some positive edge, it will change the value. So when this will change the value, then this will change value, and they will toggle, they will shift, they will change. So this is how a toggle flip-flop is made. Okay. So after the toggle flip-flop, then we consider how to connect. We consider some questions for a PT. And current transformer, how to reduce ratio error. If you want ratio error to reduce, then this magnetizing current should be as low as possible. It should be very low. Then we considered CT should never be open circuited. Open circuited should not be allowed at any time. It is not permissible, not permissible. Okay. So in that case, what we have to do, we have to connect a new ammeter and parallel to the old ammeter first, and then we must remove the old ammeter. Then I consider by measuring a high voltage using a PT and MI voltmeter, what happens? Only the ratio error is seen. The phase error cannot be measured by your MI voltmeter, because it only gives you your RMS value. Now this is the SR flip-flop, which is made of NOR gates and not XOR gates. Okay. That's for me to learn. Then there's a D flip-flop, which is event triggered. Okay, based on an event, only it will change its value. Right? So this entire thing is effectively a D flip-flop that is event triggered. Sorry. That is event triggered. Okay, so when enable is high, then only the value of D is passed on. Otherwise, when enable is low Q will, the D flip-flop output will remain at its previous value. Okay. So now we have considered how there's an enable 1 signal which is complementary to my clock. There's an enable 2 signal as well, which is in phase with my clock. Then my D is my input, which is changing with time. Now, when my enable 1 is high, then only my Q1 is same as my D. But when my enable 1 is low, it will hold on to the previous value, right? And when my enable 2 is, so then that will generate my Q1. Okay, it will generate my Q1. Then when my enable 2 is high, it will directly take the value of Q1. And when enable 2 goes low, it will hold on to the previous value of Q1. Okay. So in this way, what is happening is only at this edge, only at the falling edge, the output, this is your output, is changing its value. So effectively what is happening is this is your input and this is your output, right? But it is only changing at the negative edge of your clock. So that is why it is a negative edge trigger D flip-flop. Next, we consider the case for a AC voltage, how internal resistance, how much is the power loss, what is the reflected resistance, etc. Then we considered how a T flip-flop using a binary ripple counter is made and how we can reduce the frequency. Then we also considered for a CT, what is the power loss, which is very high in this case, as well as what is my equivalent resistance, which is very low. Okay. So with this, I will conclude the session. Thank you.
Thank you, sir. Good night, sir.
Good night.